Ready to dive in. Today, we're tackling the life cycle of stars.
Sounds exciting.
It is. I mean, I've always looked up at the night sky and, those pinpricks of light have always fascinated me.
Yeah,
But I realize I don't actually know that much about them beyond just, like, they twinkle.
right.
So let's get into it. What's more to it than just twinkling?
Well, I think one of the most mind-blowing things to start off with is that all the elements in our bodies, literally like the stuff that makes us up, can be traced back to stars. We're
Well,
these incredible cosmic factories churning out the building blocks of, well, everything.
so we're basically walking, talking constellations.
Yeah, you could say that.
That's incredible. But where does it all even begin? How is a star even born?
Okay, so picture this. These massive clouds of gas and dust.
Okay.
They're called nebulae, and we can actually see one with the naked eye, the Orion Nebula.
Oh, wow.
It's like a giant cosmic nursery full of potential.
Okay, I can picture this giant cloud. But how does it go from gas and dust to, like, a blazing star?
So gravity plays a huge role. Imagine something disturbs the nebula, maybe a shock wave from a nearby supernova. And that disturbance, it makes the gas and dust start to clump together.
Okay.
And as these clumps grow, their gravity, their pull, it gets stronger and pulls in even more material.
So kind of like a snowball effect.
Yep.
But on a cosmic scale.
Exactly. And that clump, it's called a protostar. As it keeps growing, the pressure and temperature at its core, they just skyrocket.
So it's like a star in the making, hidden away.
Hidden, but not completely. Astronomers can actually detect it because it emits infrared radiation.
That's so cool. So at what point does it actually become a star?
Well, eventually, the core of that protostar gets so hot, so unbelievably hot, something like 10 million Kelvin.
Wow.
And that triggers something called nuclear fusion, and well, bam, a star is born.
Like flipping a switch and suddenly you have this, like, huge furnace burning bright.
It's a pretty powerful analogy.
Right.
And that's when the star enters what we call the main sequence, which is basically its stable phase where it spends most of its life. Our sun has been on the main sequence for about 4.6 billion years.
So all stars live that long. Billions of years.
No, not at all. How long a star lives really depends on its mass. The bigger the star, the faster it burns through its fuel. So bigger stars actually live shorter lives. It's kind of a cosmic balancing act between its mass, how bright it shines, and its ultimate fate.
So our sun, is it kind of average then?
You could say that. It's what we call a G-type star or a yellow dwarf. Astronomers use a classification system O, B, A, F, G, K, M, M to sort stars based on their characteristics. Our sun, a G-type, falls right in the middle. It's not a massive, short-lived blue giant, but it's also not a tiny, long-lived red dwarf.
Red dwarfs are the ones that live for, like, trillions of years, right?
That's right. It's fascinating to think about the sheer variety of stars out there.
Yeah, each with its own story.
Definitely. And those stories don't end there either. Even a
Mhm.
star like our sun won't last forever. Eventually, it will run out of hydrogen, its core fuel.
Okay, so what happens when that happens?
Well, things start to change. It loses that outward pressure that was keeping it balanced, and gravity starts to win.
Okay, so gravity takes over. Then what?
The core, it contracts, heats up even more, and the outer layers, they start to expand dramatically.
Like the star starts to swell.
Exactly. That's the beginning of the red giant phase.
And how big do those red giants get?
Hundreds of times larger than the star's original size. It's pretty dramatic.
Wow. Like our sun is going to swell up like that eventually.
Yes, and in fact, it's predicted to become so large that it could engulf Mercury and Venus, and maybe even Earth.
That definitely puts things into perspective. So what's happening inside the star during this, like, swelling phase?
Well, even though the core is contracting, it actually gets hot enough to start fusing new elements. So for a star like our sun, it'll start fusing helium into carbon and oxygen.
So even though it's, like, in its twilight years, it's still contributing to, like, the cosmic recipe.
Absolutely. But what happens after the red giant phase, that depends on the initial mass of the star. It's a bit like a cosmic crossroads.
Okay, so what paths can a star take after it's a red giant?
Well, for less massive stars like our sun, they eventually expel their outer layers, leaving behind a very dense core, a white dwarf.
A white dwarf. So it's, like, small but super dense.
Yes, incredibly dense. Think of it this way. A teaspoon of white dwarf material would weigh about 5.5 tons.
Wow, that's crazy. And what about those outer layers that get expelled?
A white dwarf is the end of the line for a star like our sun.
Okay, I'm already hooked. But what about the more massive stars? They don't just become white dwarfs, right?
Oh no, their endings are much more dramatic. We'll get into those fireworks next time.
I can't wait. It's amazing to see how a star's mass determines its whole life and even its death. That cliffhanger about those outer layers, the ones that are expelled by stars like our sun,
Right.
I'm dying to know what happens to them.
Well, it's not just an ending, it's like a whole new beginning. Those outer layers, they're full of elements the star created during its life.
Okay.
And they don't just disappear, they become part of what we call the interstellar medium.
The interstellar medium.
Yeah, it's basically the vast space between stars filled with gas and dust.
So it's like the star is giving back to the galaxy in a way.
Exactly. And it's not just any old dust, it's got carbon, oxygen, even heavier elements like iron, all from the star's fusion processes.
Oh, right, because stars fuse lighter elements into heavier ones as they age.
Exactly. So this material, it's like stellar ejecta, it drifts through space, and eventually it encounters other clouds of gas and dust.
And I'm guessing those clouds are important for making new stars.
You got it. Over millions of years, these clouds, they collide and merge thanks to gravity and turbulence.
So it's like stirring a giant cosmic pot, mixing all these ingredients together.
A very slow and massive pot. But yeah, that's a great way to put it. And those collisions, they create denser regions within the interstellar medium, which become stellar nurseries.
So that's where new stars are born.
Exactly. The material in these dense regions collapses under its own gravity, heats up.
And eventually, boom, new star.
You got it. If the conditions are right, nuclear fusion ignites and a new star is born.
Wow, that's like a cosmic cycle. Stars are born from the remnants of older stars, and then they die and create the material for new stars.
And planets, too.
Oh, right, planets. I almost forgot about them. So how do planets fit into this whole picture?
Well, as a new star forms, not all the material falls directly into it. Some of it starts to swirl around the star, forming a disk.
A disk of gas and dust.
Yeah, it's called a protoplanetary disk.
And that's where planets form, right?
You're on a roll. The material in the disk, it's constantly colliding, particles stick together, and over millions of years, they grow larger and larger.
So you start with microscopic dust and end up with a planet.
It's pretty amazing. And remember those heavier elements we talked about? The ones created in dying stars?
Yeah.
Well, they're essential for forming planets like Earth.
Oh, so.
Elements like iron and nickel, they become the cores of rocky planets. And heavier elements like uranium and thorium, they create internal heat, which drives geological processes.
So they shape a planet's surface and maybe even make it habitable.
Exactly. So the death of a star, it's not just an ending, it's a key part of creating new worlds.
I'm seeing how everything is connected now. It's incredible. But speaking of dramatic endings, we were going to talk about those massive stars, the ones with the explosive fates.
Ah, yes, the supernovae. Ready for some cosmic fireworks?
Oh, absolutely. Bring on the supernovae.
All right, get ready for some serious cosmic power. When a massive star, much bigger than our sun, reaches the end of its life, it doesn't fade away quietly. It explodes in a supernova.
Supernova, they're like the biggest explosions in the universe, right?
They're among the most energetic events for sure.
But what causes them? Is it just a bigger version of a red giant shedding its layers?
It's a lot more intense than that. You see, as the star's core runs out of fuel, it can't support itself against its own gravity.
Okay.
And then the core collapses really fast with
Yeah.
incredible force.
So it implodes.
Yeah, and that implosion creates a massive shockwave that blasts the star's outer layers into space.
Wow, so it's like an implosion that triggers an explosion.
Exactly. And the amount of energy released is just mind-boggling. For a short time, a supernova can outshine an entire galaxy.
Wow, talk about going out with a bang. So where does all that material go? Does it become part of the interstellar medium like we talked about before?
It does, but supernovae do something else incredibly important.
What's that?
They create the heaviest elements in the universe. Things like gold, uranium, platinum.
So like the gold in my ring, it came from a supernova.
It's very likely. The incredible heat and pressure of a supernova are needed to forge those heavy elements. Then they get scattered throughout space.
It's amazing to think about. So we've got all this new material, heavy elements, and it all gets mixed into the interstellar medium for new stars and planets.
It's a cycle of creation and destruction constantly playing out across the universe.
I love it. But we still haven't talked about what happens to the core of the star after a supernova. What's left behind?
Well, that depends on how massive the core is. For cores that are about 1.4 to 3 times the mass of our sun, they collapse into something called a neutron star.
Neutron star. Remind me, what's that again?
Picture this: a sphere maybe 12 miles across.
Okay, pretty small.
But it has more mass than our sun. The gravity is so strong, it forces protons and electrons together, and you get neutrons.
So it's like taking our sun and squeezing it down to the size of a city.
Pretty much. A sugar cube-sized amount of neutron star material would weigh billions of tons.
That's wild. Okay, so what if the core is even more massive than that?
Then things get even weirder. For cores more than 3 times the mass of our sun, the collapse doesn't stop. It keeps going until you have a black hole.
Black holes. I've always been fascinated by them, but they're kind of hard to wrap your head around.
Definitely. It's a region of space-time where gravity is so powerful that nothing, not even light, can escape.
But if nothing can escape, how do we even know they're there?
We can't see them directly, but we can see their effects on things around them.
Oh,
For instance, if a black hole is orbiting a star, we can see the star's motion change, and that tells us something invisible is there.
it's like we're detectives, using clues to understand something we can't see.
That's a great way to think about it. And sometimes matter falling into a black hole heats up and emits X-rays, which we can detect.
So we have all these ways of figuring out that black holes exist, even though we can't see them directly.
Science is full of surprises like that.
It's amazing. So we've covered a lot of ground today. We've gone from the birth of stars in nebulae all the way to their explosive deaths as supernovae or quiet endings as white dwarfs, and then the really strange black holes.
And don't forget about the elements they create, the material for new stars and planets. We truly are connected to the stars, in a way.
I know, it's like we're part of this grand cosmic cycle, from the smallest atom to the largest supernova. This whole deep dive has really made me appreciate the universe in a whole new way.
I'm glad to hear that. Keep looking up at the night sky and remembering all the amazing things happening out
I
there.
will. And thanks to all of you for joining us on this deep dive into the life cycle of stars. Until next time, keep exploring and stay curious.